Welcome back to the Mechanics of Solids lecture series. We're looking at examples calculating peak bending stress with extension to beam design. This next example is a beam design application. This is a problem from Mechanics of Materials by Timothy Philpott, Wiley 3rd edition. It reads, the beam shown in the figure will be constructed from a standard steel HSS shape using an allowable bending stress of 30 KSI. At the moment, we don't know what the cross-sectional properties are, but we want to select a suitable cross-section that will meet the criteria. We're asked to develop a list of 3 acceptable shapes that could be used for this beam, choosing from among HSS 8, HSS 10, and HSS 12 shapes. Then we want to choose the overall most economical HSS shape for the beam. HSS stands for hollow structural section. In the real world, there are many different standard HSS sections to choose from. However, for this problem, we'll consider a small subset of those sections that are found in an appendix in the back of your book. An HSS section is basically a hollow rectangular section. Looks something like this. According to the chart, the largest dimension will be called the depth, D. The dimension in the cross direction will be called the width, B, and then the thickness will be labeled T. So the designation for HSS, the first number in the chart is the depth, the second number is the width, and the third number is the thickness in inches. Another important thing to note is the weight per unit foot. That's a measure of the economy. In general, you want to choose the lightest section that you can, which will have the least amount of material. You could also look at the cross-sectional area. Weight and cross-sectional area should be proportional. In terms of design, we'll assume bending about the strong axis, which in this case, if the beam is taller than it is wide, the chart is assuming the x-axis to be the outward and y-axis pointing up. So what we're used to calling I sub z is referred to or is equivalent to I sub x in this table. So the strong dimension properties located in this column right here. So let's return to the calculations for a minute. In order to solve this problem, just like the previous one, we need to calculate the bending moment diagram to determine the overall maximum moment in the beam. Since this example is very similar to the last one, I'm going to take some shortcuts. I'll note that the reactions are 13.5 kips at A and 23.5 kips at B. I'll make a quick sketch of the shear and bending moment diagram. Here's the shear force diagram. V in kips, jumps up to 13.5, drops down linearly to 18.5, jumps back up to 5, and comes over and back down. That's the shear force diagram. Bending moment diagram. Moment in kip feet starts from 0 at the left end, comes up to a maximum, drops back down, and comes back up. And the values of the maximum moment and the minimum moment can be calculated from the areas of the shear diagram, which very quickly I'll denote this length here is 6.75. The length on this side is 9.25 feet. The area A1 is equal to 45.56, which happens to be the value of the maximum moment. The area of this triangle down here, A2, is equal to 85.56. Subtracting that from the maximum moment gives us the value down here of 40. And then the value of this third area, A3, is equal to 40, so the moment diagram comes back to 0. All these calculations were used to determine that my maximum moment over the entire beam, and I want the magnitude here because it's a symmetric cross-section, a maximum moment is equal to 45.56 kip feet. Okay, so for design, we want to choose the cross-section properties that will satisfy the criteria, which is that sigma max must be less than or equal to 30 KSI. That's the allowable stress. So we'll say sigma allowable equals m c over I, where or equivalent to m over s, where s is the section modulus equal to I over c. So the section modulus in one parameter takes account all the information about the cross-section that is needed to compute the stress. So this is why it's a convenient parameter for design. In order to pick a suitable section, we need to basically invert this equation and solve for s. We get the required section modulus for the beam has to be greater than, or equal to the maximum moment divided by sigma allowable, or 45.56 kip feet times 12 inches per foot divided by sigma allowable, or 30 KSI. This gives it a required section modulus of 18.24, and the units, kip feet divided by KSI, units should be inches cubed. Okay? So going to the next, back to the next slide, the chart, and remember our requirement that S required equals 18.24 inches to the cube, inches cubed. We can identify some suitable sections that will work. And I'm going to switch over to highlighter in order to do that. Okay, I'll just start with SX and go down the chart. 55.6, this one will work, this one will work, this one will work, this one will work. This one, this one, this one, this one. So everything in the 12 series and the 10 series will work for this example. However, moving further down the chart, we see that the next few do not work because their S values are lower than the required S. So in terms of acceptable sections, any in the first two. Now, the ones that are more economical are going to be the ones that are lighter. So as we move down the chart and look at pounds per foot, the lowest one in every row is the lightest one. So among the 10 series, this one would be the most economical, the HSS 10 by 4 by 3/8. Among the 12 series, if we look at the total weight, the bottom one would be the most economical, HSS 12 by 6 by 3/8. And perhaps you can already see for yourself which one is the overall most economical section. It should be the one that's the lightest, has the lowest weight in pounds per foot, and the lowest area, and that would be the HSS 10 by 4 by 3/8. So most economical equals HSS 10 by 4 by 3/8, and that's the best answer for this problem according to the criteria that we're given.